Lesson number 9 talks about hypothesis testing. The items needed for this lesson are your TI-83 calculator and the T-chart. I name it the edited version, and that looks something just like we did in the last chapter, right? There's the omit section on the bottom, and then there's your 90, 95, and 99% confidence intervals for the T-chart. So we're going to need that for this lesson. A little background information. So a typical hypothesis test question states an average or percentage for something, and you would like to see if this average or percentage is still true for the current population. So you conduct a sample, excuse me, and calculate its average or percentage. You now compare your sample to the previously stated average and either conclude that they are the same, or you say that they are far apart enough to say that they are different. This close enough versus far apart creates a gray area. Say you're being picked to go up on it to go on a date at 8 o'clock, and your friend is running late. How much time will you wait until you conclude enough time has passed and you will not wait any longer? For some people it may be 10 minutes, or others it may be 30 minutes. This is where in hypothesis testing a significance level called alpha plays a role. The significance level determines the cutoff or critical value of a hypothesis test. You place this value of the significance level in the tail of a bell-shaped curve and use the T-chart to determine the z-score, which is called the critical value for the hypothesis test. You then determine if the hypothesis is accepted or rejected based on the sample z-score from the statistics in question. I will demonstrate with a bunch of examples. We're going to do that in just a second. Let me make one little correction here. The z-score is actually called the test statistic. That's my fault. I didn't type that in correctly, so I'm going to correct it. So the z-score is called a test statistic. All right, here's the steps we're going to do for all these questions. Step 1, we're going to state what they call H sub O, which is called the null hypothesis, and H1, which is called the alternate hypothesis. We're going to draw a bell-shaped curve. We're going to label the exception and rejection regions, and we're going to place the significance level in the tail, and we're going to use a T-chart to find a critical value. All this we're going to do on a bunch of examples. I know it seems a little weird now, but once you do a few examples, you'll see what we're talking about. Find the mean for step 2 and standard deviation of the sample. Make sure you use the correct formula for standard deviation based on if the question is a value or percentage. Step 3 is find the z-score for the sample. This z-score is called the test statistic in hypothesis testing. And then finally, step 4, place the test statistic in the correct area of the bell-shaped curve based on the critical value and make a brief conclusion. Well, see, generally, hypothesis testing, like we talked about just a second ago, is you have yourself a curve, and the mean that they tell you is going to go here, and then it depends if it's a left-tailed or a right-tailed test. If it's a right-tailed test, then there's what they call a critical value. Now, this critical value is very important. This determines if you're going to either accept or reject HO. Accept HO always goes before the tail, and reject HO always goes in the tail. Always in the tail. So you're allowed a little leeway here. The leeway is you can be different from the mean only up to a certain point, and then once you get to that point or beyond, then you're going to say, nope, things have changed, and so you reject what they call HO, which is the null hypothesis, which is what was previously stated in the question. And if you tie the line is always reject. That's very important to remember. So let's do some examples, and then you'll see from examples how this works. So example number 1. We have the crime statistics from a local town state 15% have been a victim of some sort of crime in the past 5 years. The statement is always your null hypothesis in the question, which is called HO. So that's always, whatever they tell you, that's always considered the null hypothesis. You always assume the null hypothesis is true unless something comes along and proves it not to be true. So a recent sample of 890 locals found 12% claim to have also been the victim of some sort of crime in the past 5 years. Perform a hypothesis test to determine if the percentage of local crime is decreased. So the key word there is decreased. Decreased tells you that this is a left-tailed test because anything left of the mean would be decreased. Decreased is always left. If it said increased, that would obviously be right. So we're going to go through the steps that we just had in the last page. Step number 1 says determine your null hypothesis. So we're going to say our null hypothesis is what they stated originally in the question, 15%. The alternate hypothesis is based on what type of tail you have. This is a decreased, so it's a left-tailed test. So if you're left of the mean, that means you are less than whatever they told you. So be less than 15%. This creates a left-tailed test where your mean goes here. Okay. You have an acceptance region, so you're going to say I accept HO or reject HO, and reject always goes in the tail. Your significance level that they state in the problem, so for part A it asks for 1%, always goes in the tail. Okay, so that's basically everything that we just did a second ago. You always state HO and H1, you draw yourself a bell-shaped curve, you put in the critical value, which is dependent on what type of test it is. Alpha always goes in the tail, reject HO always goes in the tail, accept HO always goes not in the tail. Now what we need is we need to know what is this critical value, which is the cutoff line. Now of course the mean has a z-score of 0 because that's always the mean. This is based on a couple things. First, our recent sample, we have 890. So our sample size here is 890 individuals. And we have a area in the tail of 1%. So when we go to our t-chart and we look where it says area in the right tail or left tail, we're looking at 0.01, which is 1%. So we're going to look at 1%, and then we're going to, because the sample size is 890, we're going to go all the way to the bottom because that's where we said our sample size was greater than or equal to 30. And we're going to get back 2.326. So this is a z-score of 2.326. It's negative because we're on the left, and that's going to be our cutoff. So any value from 0 up to that would be in the acceptance region, and then anything that line or over is going to be in the rejection region. So now what we have to do is we actually have to conduct our sample. So we need to find the z-score for the sample. And based on what that z-score lands, we'll either accept HO or reject HO. So we have a mean. Now this is a percentage question, so mu sub p hat. And where it says in the question, it says a recent sample of 890 local adults found 12%. So that's our mean. So we're going to write down 12%. Standard deviation, because it's a percentage, sigma sub p hat, p 12 times q 88 divided by sample size of 890. So in our calculator, we're going to put in the square root, 12 times 88 divided by 890. And we're going to get back 1.09. And that's our standard deviation. Now we need to find the z-score. So we're going to say data minus mean divided by standard deviation. Now the data is going to be your sample mean, and the mean is the original stated mean. So for this example, we're going to say our sample mean is going to be 12%. Originally it was said it was 15%, and we're going to divide that by 1.09. So in our calculators, we're going to put in 12 minus 15. We're going to divide that by 1.09. We're getting back negative 2.75. That is the z-score for our sample, and specifically for our hypothesis testing, that is called the test statistic. Now we're going to place the test statistic. Depending on where the critical value is, it's going to either end up, in this case, left of it or right of it, and this is like a number line. If this is 0, and then this is like -1 and -2 and -2.1, -2.2, then -2.326. Where does -2.75 lie? It lies left of the cutoff. Left of the cutoff ends up in the tail, and the tail is reject. So we're going to write down here our conclusion is to reject HO. And then that means we're going to conclude we're going to reject this, which means we're going to accept this. And so we're going to say that the statistic is less than 15%. So if you look at the question, they said recently 15% had stated they'd been the victim of some sort of crime in the past 5 years. More recently, they found 12. So you want to know, has the what was previously thought percentage gone down? And you're going to say, well, according to us, it has. It's gone past what we consider to be an acceptable difference, and we reject HO, which means it has decreased, so it's less than 15. The only thing that changes now is basically depend on what you want to put as far as a significance level in the tail. So we have 2.5%. We draw ourselves a new bell-shaped curve, and it's still a left-tail test. Everything here is still accept HO. The tail is still reject HO. The only difference now is alpha is 2.5%. The mean is still a z-score of 0. So we changed the percentage in the tail, which is the rejection region, and that's just going to change this cutoff value. So now in our t-chart, we look under a different column, which is 2.5% in the tail, and because our sample size is more than 30, we go to the bottom and we get back a new critical value of 1.96. That's to the left, so we mark it as a negative 1.96, and we call that our new critical value. And that may or may not change the answer, depends on what we got. Now our sample size is negative 2.7. Our sample test statistic is negative 2.75. That also is left of negative 1.96, which gets you in the tail, which is reject. So for this one, we're also going to say we reject HO. And that means that we're going to reject again 15, which means we're going to say it is less than 15%. Now, most textbooks don't use the terminology accept HO and reject HO. I like to use this because I always say to my students, reject HO always goes in the tail. That's just always the way it is. But what normally happens is on textbooks, accept HO, the language for accept HO is always fail to reject HO. But of course, if you fail to reject, you're really accepting. I just don't really like that terminology, fail to accept. I'd rather just use a very straightforward accept HO. And then if we conclude reject HO, that's fail to accept HO in most textbooks. But in my teaching, I don't like to use this, fail to reject, fail to accept. It seems too obscure, so I'd rather just go straightforward, accept HO, reject HO. For these two examples, they're both reject HO. And there you go. Now this changing of the critical value is pretty similar to like if you pick somebody up on a date. So let's just think of this scenario. Somebody wants to pick you up to go out. Let's say you tell them 8 o'clock. And you have a cutoff value for being late. And let's say you decide that it's 8:30. And so anything from 8 to 8:30 you're going to go on the date. Anything 8:30, which is the cutoff, and later you're going to say, no, I reject the going on the date. So your acceptance region is still here, your rejection region is still there. Well, see, this cutoff value can change depending on who you talk to. You may ask another person, you want to get picked up at 8 o'clock, but they may have a different cutoff. You may allow 30 minutes where maybe they allow only 15 minutes. And you'll notice that the cutoff line changes depending on the scenario that we have. And that's what we're doing here. And it's based on the alpha. So if we have 1%, we get a critical value. If we change the alpha, we get a different critical value. That's all. And then you base your accept and rejection on that critical value that's created. So let's do a bunch. We're going to do about 6 problems. And in those 6 problems, hopefully by the time we get through like 4 and 5 and 6, you got this down pretty good. So number 2. The average local response time for emergencies in a city is 7.6 minutes. So that's the stated, that's HO. A recent sample of 75 emergencies found a response time to be a mean, X bar, 8.2 minutes with a standard deviation of 2.75 minutes. Okay. Perform a hypothesis test to see if the response time has increased. All right, the key word there is increased. That means increased or more than. If you're looking at a mean in the middle, increased would be always to the right, so this is a right-tailed test. And here we go. We're going to set up our null hypothesis. Null hypothesis is what is originally stated, 7.6. Your alternate hypothesis is then either going to be more than or less than that value. So in this case, it's a right-tailed test. So we're going to say it's more than 7.6. You never ever state what they found. Okay, it's always what they told you or more or less than what they told you. We create a bell-shaped curve. We label the mean to be 0 in the middle. We have ourselves a cutoff on the right because it's a right-tailed test. Everything in this region is accept HO, and the tail is always reject HO. We place alpha in the tail, and so for part A it asks for a 1% significance level, so we're going to say we want 1, and that is going to help us find a critical value. So our sample size, if you notice, is 75. That's more than 30. So in our t-chart, to find that critical value, we're going to ask for the tail, which is 1%. So we're going to go to 0.01, and then we're going to go down based on the degree of freedom. But because our sample size is 75, we're going to follow this all the way to the bottom because it's more than 30, and we're going to get back 2.326. And there it is. And so we're going to say the cutoff is 2.326. Okay, so that sets up anything between 0 and this number is accept, anything that number or more is going to be reject. So then we find our sample z-score. So our sample has a mean. In this case it's a value question because we're talking about minutes. So mu sub x bar is 8.2 right here, that's our mean. Our standard deviation sigma sub x bar is the standard deviation that they told us, 2.75, but we have to divide that by radical sample size because it's a sample. So in our calculators, right here, we'll clear that off. We're going to put in 2.75 and we're going to divide that by the square root of the sample size. 0.317, let's round that to 0.32. And that's our standard deviation. Now we want to find our z-score. So data, which is our sample mean, 8.2, we're going to subtract the mean, which they stated was 7.6, and we're going to divide that by our standard deviation of 0.32. All right, so 8.2 minus 7.6, we're going to divide that by 0.32. We're getting back 1.875. Let's round that to 1.88. So we always use 2 decimal places for consistency. That is called, because the textbook always uses these terms, our test statistic. If you say that backwards, it's the statistic used to test our hypothesis. Now, where does 1.88 lie with a 1% significance level? 1.88 is slightly less than the cutoff of 2.326. So that lies left of the cutoff, which is in the exception region. So for part A, we're going to say we accept HO, and HO we said was what they told us, originally 7.6 minutes. So I write down something like it's still 7.6 minutes, or it hasn't changed from 7.6 minutes. So what we're saying is, if the average local response time is 7.6, but we recently had found 75 emergencies where the average was 8.2. See, if you're like in charge of some kind of town services, some people in the town may say, well, whoa, the emergency time has gone up. And you would then respond, well, that was based on a sample, and it has not gone up significantly. That's the key term, because you really didn't go past the cutoff. It's like being late on a date. You're a little late, but you weren't significantly late. We were a little bit more than the average, but not significantly more, where we would say that the average has somehow changed. All right, so for part B, the only thing that changes now is we just draw ourselves another bell-shaped curve. Everything here is still accept HO. Everything in the tail is still reject HO. The average in the middle is always 0. The only difference is now we change the alpha, or significance level, in this case to 2.5%. So we look up at a different column in our t-chart. So 2.5 in the tail. They sampled 75 emergencies, so we're going to go all the way to the bottom, and we're going to say 1.96, because that's where the sample size is more than 30. Put that off on the side. So we're going to say 1.96 is our critical value. Where does our test statistic, Now this doesn't change because this is still our sample mean and standard deviation, and this is still the z-score. That doesn't change. So, but now where does 1.88 lie? And you're going to say 1.88 lies still left of 1.96. Think of this as a number line, which is still in the exceptions region. So we're going to say we accept HO. And so we're going to say it's still 7.6 minutes. Part C changes again the alpha. If I scroll down just a little bit here, 5%, we make a new alpha 5%. So we put 5% in the tail. This is still accept HO. This is still reject HO. The mean is a z-score of 0. In our t-chart, we're going to now have 5% in the tail. We're going to go all the way to the bottom, and we're going to get back a 1.645. That's our critical value, CV for short. And our test statistic is still 1.88. 1.88 would lie in this case more than 1.645. That ends up beyond the cutoff, which is going to be in the tail, and the tail is reject. So you're going to reject HO. So let me scroll up again. You're going to reject this, and so you're going to say its alternate is true, which is now it is more than 7.6 minutes. So everything is based on a significance level. So again, if you're at a town board meeting and people are complaining that the response time has increased, if somebody on the board says no, it hasn't increased significantly, you could argue actually it has. And again, it's an argument based on what your alpha is in the tail. No different than if somebody shows up late for a date and at 8 o'clock you're supposed to show up. If the person shows up at 8:20, some people will say, nope, that's okay. That's still within an allowable difference of 8 o'clock. Some people may say 8:20 is too late and I really don't want to go now. It all depends on your perspective of what the cutoff value is. All right, so let's look at another example. All right, so number 3. The national average for salary for correctional officers is $47,193. So that's what's stated, so that's your null hypothesis. In Syracuse, New York, the average salary for a corrections officer based on a sample of 56 officers is a mean X bar, this, and a standard deviation of this. Is the average salary for Syracuse correctional officers less than the national average? All right, so less than tells you also it's a left-tailed test. All right, so here we go. We're going to label our HO. Our HO is what they stated, which is the salary is $47,193. The alternate hypothesis is going to be a left-tailed test, so that means is it less than $47,193? Okay. We're going to draw ourselves a bell-shaped curve. We're going to cause a critical value on the left-hand side. Everything here is accept HO. The tail is reject HO. And we're going to place that alpha in the tail, which is 1%. Okay. And these are actually going to be exactly the same as the last question in terms of cutoff values. We're going to go to the t-chart. Our sample size is right here, 56. So when we go to the t-chart, we go to 0.01, we go all the way to the bottom, we get back 2.326 is our critical value, because that's to the left, that's a negative, and that's the z-score. Okay, so only thing left is now we have to find our sample. Where does our sample z-score lie in relation to this setup here? So you're going to say we need a mean. This is salary, so it's mu sub x bar. They're saying that the salary of the correctional officers in Syracuse is $43,516. The standard deviation is the standard deviation 17,160, but we have to divide that because it's a sample by the square root of 56. So 17,160 divided by radical 56. Okay? 17,160. Whoop, there we go, sorry. Divided by the square root of 56. Okay, 2293.10. And then our z-score, data, that's our sample mean, minus the mean, which is what was stated, divided by the standard deviation. Okay, that's a 9. So 43,516 minus 47,193. We're going to divide that by 2293.10. Negative 1.60. That's called our test statistic. Now we place the negative 1.60 depending on the critical value. In part A, with a critical value of this, we end up right of that. So that's going to be in the accept HO region. And if you accept HO, that means you're accepting that it's still 47,193. So even though in Syracuse they said the average is 43,000, it's not significantly lower than the national average. So you would say, nah, it's still pretty close to the national average. Okay. And why people say, well, no, that's based on a sample. So that's why this whole thing. If they had asked all corrections officers in Syracuse, and you got back that, then you wouldn't do a hypothesis test. A hypothesis test is done when you have a sample, because samples aren't foolproof. All right, so part B, the only thing that changes is now the significance level. So if we have a 2.5% significance level, we go in our t-chart down 2.5 and we get back a negative 1.96 critical value. Where does negative 1.60 lie? You're going to say, well, it lies to the right of negative 1.96. So you're going to say, I accept HO also in this scenario. And you're going to say, nope, it's still 47,193 because you're to the right of the cutoff value. And then part C, they're asking for, let me scroll up, there's 5% in the tail. So if we put 5% in the tail, in your t-chart, look at 0.05, go all the way to the bottom, you get back negative 1.645 because it's a left tail test that's negative. Where does our test statistic of negative 1.60 lie? Well, pretty close, but negative 1.60 still lies a little shy, but very, very close though, because there's negative 1.60, then negative 1.61, 1.62, 63, and then negative 1.64. So you're to the right test statistics. So that's in the accept HO. And so for this one also, we would say we accept HO, and we are still 47,193. So we're still around the national average, those in Syracuse. Some students always ask me, why do you change the alpha? Well, when you take statistics, this is a general statistics class, but we have a lot of different programs in this class. The significance level changes. Typically, the most common significance level is 2.5%, but in the nursing field, they use 1%. Sometimes in the business field, sometimes they use 5%. Criminal justice field, a lot of times they use 2.5%. So we have to kind of adjust our thinking to different programs. And you as students out there understand that, not everybody's taking the same program. So I have to change the significance levels. So number 4. We have a trucking company, and a trucking company has decided to place Easy Pass tags in all trucks to see if the transportation time will be decreased, left tail test, because there'll be less time to wait at the tolls. Prior to the Easy Pass installations, the truck company was averaging 323 minutes for a certain route. So that's the assumption, that's our null hypothesis. So HO is 323 minutes. Because we want to know if it's decreased, then H1 is going to be less than 323 minutes. After the Easy Pass installation, a sample of 49 trips on the same route averaged 317 X bar with a standard deviation of 26. So we want to know, is 317 significantly less than 323? Now let's test this claim to see if it's decreased. All right, so for part A. we need to draw ourselves a bell-shaped curve. It's a left tail test. Mean is always 0. Accept HO is always to the right in this case. Reject HO is always in the tail. We place our significance level for part A, which is 2.5%, in the tail. We take a look at our sample size, which our sample size, it says, was 49 trips. And you're going to realize in just a second here, 49, of course, is more than 30. So 2.5 is the area in the tail based on the significance level. We go down the degree of freedom, but because the sample size is 30 or more, we're going to go right here, and we're going to say 1.96 is our critical value. 1.96 CV. We make it negative because you are left of the mean. And that sets up our scenario. So anything within here is accept. Anything at the number or less than is going to be reject. All right, so we find ourselves, for our sample, we have a mean, mu sub x bar, which is 317 minutes. We have our standard deviation sigma sub x bar. That's the standard deviation of 26 divided by radical sample size. They said the sample is 49 trips. So 26 divided by radical 49. 3.71. And then we have to find ourselves a z-score. Data 317 minus the mean, they told us was 323. And we're going to divide that by 3.71. 317 minus 323 divided by 3.71. Negative 1.62. Okay. That is called our test statistic. We place this, and it ends up being to the right of our critical value, which is in the acceptance region. So we're going to say we accept HO. And so we're going to say it's still 323 minutes. Even though our sample ended up with a value of 317, it's a little less, but it's not significantly up to the critical value less. So we're saving a little time, but really not anything significant. Part B asks us, let's test it again, but let's pick a different alpha in the tail. Let's pick an alpha 5%. So accept HO. The tail is going to be reject HO. The mean is a z-score of 0. There we go. We want a 5% in the tail. So our t-chart, we're going to go to 0.05. Our sample size was more than 30, so we're going to go to the bottom, and we're going to say 1.645. Where does our test statistic of negative 1.62 lie? Slightly to the right. And so that is in the accept HO. And we're going to say it's still 323 minutes. But we're getting closer to that critical value. So part C, if we scroll up again, part C asks first, let's do an alpha to be 10%. Okay, this is accept. This is reject. In our t-chart, 0.10. Okay, sample size was 30 or more, so 1.282. Make it negative because it's on the left. That's our critical value. And so for this case, we had a test statistic of 1.62. Our test statistic of 1.62 is going to lie beyond the critical value. That would end up being rejection region, so we're going to reject HO. And so we're going to say we reject this, we're going to accept its alternate, which is going to be less than. So now we are saying, well, no, we actually did save time. Now again, the textbook is never going to say reject HO. The textbook is going to say fail to accept. If you fail to accept, then it means you're rejection. you're rejecting. I'm just going to simply say, and for your exams, I'm going to say accept HO and reject HO. I will have a question that says another way of saying reject HO would be fail to accept, and I may have a question instead of accept HO, it'll be fail to reject HO. So that'll be a multiple choice question where I simply ask what's another way of saying accept HO, and you're going to just choose that as its option. All right, hopefully you're getting better at these. So here's a fifth one. Again, for a lot of these, what I'd like you to do is I'd like you to read these. I'd like you to pause the video, and then I'd like you to have you do these problems yourself, and then come back and see if you actually got exactly what I did after I work it out for you. So here's another one. A male civilian incarceration rate for white men aged 20 to 34 in the United States with less than a high school degree was 8% in 2000. In 2008, based on a sample size of 1,063, it was 12%. Test to see if the incarceration rate for white men is less than, okay, oh, I'm sorry, with less than a high school degree has increased. So that would tell you that it's right tail test. And what they stated was the male civilian incarceration rate is 8%. So there's your null hypothesis. They're telling us 8%. They want to know, has it gone up? It went to 12. So is that significantly more than 8%? Right tail test. The mean is always a z-score of 0. Accept HO, and then in the tail is always reject HO. We take our significance level to be 2.5%. Okay. We take a look at our sample size, and our sample size is 1,063, so obviously that's greater than 30. So in our T-chart, we go to area in the tail, 2.5%, 0.025, and we go all the way to the bottom, because our sample size is 30 or more, and we're going to get back 1.96. And that's our critical value. Okay, for our sample, mean, percentage question, so I'm using p-hat. Based on a sample, there it is. Based on a sample, they got back 12%. So that's our sample mean. The standard deviation is the square root of p, 12, times q, 88, divided by the sample size, which was 1,063. Square root 12 times 88 divided by 1,063. 0.9967. Well, 0.996 is going to round that up to a 1. 0.00, or simply 1. We need a z-score. Data, that's your sample mean, which is 12, minus data minus mean. The mean is the previously stated 8, and we're going to divide that by 1.00. All right, 12 minus 8 divided by 1. Okay, 4. That's our test statistic. We place this. 4, or 4.00, definitely lies right of 1.96. That ends up in the tail, which is the rejection region, so we reject HO. So we reject that it's 8, and we're actually going to say it's more than 8. So the white male incarceration rate for men aged 20 to 34 in the U.S. has significantly increased in 2008 based on what it was in 2000. It has significantly gone up. Has it gone up significantly if we change the significance level to be 5%? Okay, 5%. T-chart, 0.05. Go all the way to the bottom because our sample size was 30 or more, so we get it back at 1.645. Our test statistic, our z-score for the sample is 4. 4 is beyond 1.645. That ends up in the tail, which is the rejection region. And so we're also going to say we reject HO, and then we can either say it's greater than 8%, or it's more than 8%, or it's increased from 8%. They all mean the same thing. So male civilian incarceration rate has increased for men aged 20 to 34 in the U.S. With less than a high school degree. Okay. Next question is, here we go. Let's do the male civilian incarceration rate for black men aged 20 to 34 in the U.S. with a high school graduate degree was 7% in 1990. In 2008, so this is what was stated, so that's our HO, 7%. In 2008, based on a sample size of 925, it was 9%. Test to see if the rate has increased. So there's our alternate. Has it gone up from 7%? So it's a right tail test. Okay, here we go. Draw ourselves a bell-shaped curve. Right tail test. The average is 0. Accept HO. Reject HO. And alpha, we're first starting off with an alpha to be 1%. The sample size, 925. So in our T-chart, 0.01, go all the way down, 30 or more, we get 2.326. Okay, our sample. This is a percentage question, so our mean, okay, right here, based on a sample, we got back a sample of 9%. So 9 is our sample. Standard deviation, it's a percentage question, so 9 times 91. 9% were incarcerated, 91% were not. Divided by the sample size of 925. That's not a decimal point there, by the way. That's just 9. Okay. Square root. 9 times 91 divided by 925. Let me show you there. 9 times 91. 0.94. Now we need a z-score. Data 9 minus the mean 7 divided by standard deviation 0.94. 9 minus 7 divided by 0.94. 2.13. Test statistic. 2.13 is to the left of the critical value. That's going to end up in the accepting region. So we accept HO, and we're going to say it's still 7%. So if those in the community argue that the incarceration rate for this type of person has gone up, you can argue, no, it has not. It has not gone significantly up. I understand it went from 7 to 9, but that was not a significant increase because it's not up to the critical value. So part B now, we're going to ask the same question. We're just going to change this critical value based on a new significance level of 2.5%. So we take 2.5%. We get a new critical value. So 0.025 T-chart. Go all the way to the bottom, 1.96. And we go all the way to the bottom because the sample size was more than 30, because in this case the sample size was 925. Okay, our z-score is right here, 2.13. 2.13 is beyond the critical value to the right. The right is always the tail, which is reject. So we are going to reject the null hypothesis. And so we're going to then say H1. So we're going to say it's more than 7%. So now we're saying it has gone up in that scenario. Part C, change the alpha now to 5%. In our T-chart, if we look at 0.05 and go all the way to the bottom, we get back 1.645. We have a test statistic of 2.13. 2.13 is to the right of 1.61645. That's going to be in the tail, which is reject. And then we're also going to say again, it's more than 7%. So there was the question. So for this one, we're going to accept. For this one's reject. For this one's reject. On a test, we're looking, I'm going to have a scenario like this, but then I'm going to ask you for each part on a multiple choice question. I'll ask you, what is the null hypothesis? What is the alternate hypothesis? What is the critical value based on a certain significance level? What is the mean? What is the standard deviation? What is the z-score? And then finally, what is your conclusion? And then I could also ask if instead of saying accept HO, you would say fail to reject HO. Same conclusion, just different way to word it. And that's the kind of questions we would do on a test. You know, we just break it down one step at a time. All right, so that's your introduction to hypothesis testing. The next section is going to be an extension of hypothesis testing.